We're told nothing escapes a black hole, not even light. But black holes still have gravity. They pull on stars, warp space, and even merge with other black holes. So, what gives? If light can't get out, how can gravity? This is one of the most puzzling questions in physics, and it reveals something profound about the nature of reality itself. When we look up at the night sky, we see stars orbiting around invisible giants at the centers of galaxies. We detect gravitational waves from black holes colliding billions of light years away. We watch as light bends around these cosmic monsters, creating rings of fire in space. But here's the thing that doesn't make sense at first glance. Black holes are defined by their event horizons, the point of no return where nothing, absolutely nothing, can escape. Not matter, not energy, not information, and definitely not light. The escape velocity at the event horizon equals the speed of light, and since nothing can travel faster than light, nothing gets out. Yet somehow, these same black holes reach across vast distances of space to grab onto stars and planets. They bend the path of light rays that pass nearby. They create gravitational lenses that magnify distant galaxies. They even slam into each other, sending ripples through the very fabric of space-time that we can detect here on Earth. This seems impossible. How can something that traps everything inside still influence everything outside? How can gravity escape when light cannot? This apparent contradiction has puzzled students and scientists alike for decades. The answer, as we'll discover, isn't that gravity somehow breaks the rules and escapes from black holes. Instead, it reveals something much more fundamental about what gravity actually is. The question itself is based on a misunderstanding, a remnant of old ideas about how the universe works. To solve this mystery, we need to abandon our everyday intuitions about forces and fields. We need to think about space and time in a completely different way. We need to understand that gravity isn't something that travels from one place to another, but something much stranger and more beautiful. The journey we're about to take will change how you see the universe. It will show you that the very stage upon which all physics plays out, space-time itself, is far more dynamic and mysterious than you ever imagined. And it will reveal why asking how gravity escapes a black hole is like asking how a bowl holds water when the water can't climb out. To answer this paradox, we first need to ask a more fundamental question. What exactly is gravity? For over 200 years, we thought we understood gravity perfectly. Isaac Newton gave us a simple picture in 1687. Every object with mass pulls on every other object with mass. The force gets stronger with more mass and weaker with distance. It was elegant, mathematical, and it worked brilliantly for predicting planetary orbits and falling apples. But Newton's gravity had a strange property that bothered physicists for centuries. It acted instantly across any distance. If the sun suddenly vanished, Earth would immediately fly off in a straight line, even though the light from the sun's disappearance wouldn't reach us for 8 minutes. This instantaneous action at a distance seemed to violate the fundamental rule that nothing travels faster than light. Then, in 1915, Albert Einstein changed everything with his theory of general relativity. Einstein realized that Newton's picture was fundamentally wrong. Gravity isn't a force at all. Instead, it's the shape of space-time itself. This idea is so radical that it's worth pausing to really understand it. We're used to thinking of space as an empty stage where matter performs. 3 dimensions of space, 1 dimension of time, all separate and absolute. But Einstein showed that space and time are woven together into a single 4-dimensional fabric called space-time. Here's the key insight that revolutionized physics. Matter doesn't just sit in space-time, it actually bends and curves space-time. The more massive an object, the more it warps the geometry around it. And here's the beautiful part. Objects moving through this curved space-time follow the straightest possible paths, called geodesics. What we experience as gravitational attraction is really just matter following these curved paths through warped space-time. When an apple falls from a tree, it's not being pulled by a mysterious force. It's simply following the straightest possible path through the curved space-time created by Earth's mass. From the apple's perspective, it's moving in a perfectly straight line. It's space itself that's curved. Think about it this way. Imagine you're walking across a perfectly flat field, trying to reach a distant landmark. You walk in what feels like a straight line, but now imagine the field isn't flat. Instead, there are gentle hills and valleys that you can't see because you're an ant walking on the surface. Your straight line path would curve around these invisible hills, even though you never change direction from your perspective. This is exactly what happens with gravity. Massive objects like stars and planets create invisible hills and valleys in space-time. Other objects simply follow the straightest paths they can through this curved landscape. We call it gravitational attraction, but it's really just the geometry of space-time itself. The mathematics behind this are surprisingly elegant. Einstein's field equations tell us exactly how mass and energy curve space-time, and how that curved space-time determines the motion of everything within it. The equations reveal that space-time isn't just a passive backdrop for physics, it's an active participant. Matter tells space-time how to curve, and curved space-time tells matter how to move. This creates a beautiful feedback loop. The sun's mass curves space-time around it. Earth follows the straightest possible path through that curved space-time, which we observe as an elliptical orbit. But Earth's own mass also curves space-time slightly, and this tiny effect has been measured with incredible precision. Even the orbit of Mercury shows minute precessions that match Einstein's predictions exactly, effects that Newton's theory couldn't explain. Now here's where black holes become fascinating rather than paradoxical. A black hole isn't an object that somehow broadcasts gravitational signals from its interior. Instead, it's an extreme example of curved space-time. The mass that collapsed to form the black hole created such a severe warp in space-time that the curvature becomes a permanent feature of the geometry. Picture space-time as a stretched rubber sheet. Place a bowling ball in the center and the sheet curves downward, creating a deep well. Roll a marble nearby and it will spiral around the well, following the curved surface. Now imagine the bowling ball is so dense that it creates not just a dip, but an infinitely deep hole that punches right through the sheet. That's analogous to what a black hole does to space-time. But here's the crucial insight that resolves our paradox. The curved space-time around the black hole exists outside the event horizon. The gravitational effects we observe, the bending of light, the orbital motion of nearby stars, all of these happen in the curved space-time outside the black hole, not inside it. This geometric view of gravity explains so much about what we observe in the universe. When the Hubble Space Telescope captures images of gravitational lensing, showing distant galaxies stretched and magnified into perfect rings around massive clusters, we're seeing light following curved paths through warped space-time. The light isn't being pulled or deflected by a force. It's simply traveling in straight lines through curved space. The effect is so predictable that astronomers now use gravitational lensing as a tool. They can measure the total mass of galaxy clusters by observing how much they bend background light. They can even detect dark matter, invisible mass that reveals itself only through its gravitational effects on space-time geometry. When astronomers measure the orbits of stars around the supermassive black hole at the center of our galaxy, they find perfect agreement with Einstein's predictions. These stars aren't being yanked around by mysterious gravitational signals broadcast from inside the black hole. They're following geodesics, the straightest possible paths through the curved space-time geometry that exists around the black hole. One star, called S2, has been tracked for over 20 years as it completes its elliptical orbit around Sagittarius A star, our galaxy's central black hole. At its closest approach, This star reaches speeds of over 7,000 kilometers per second, fast enough to circle Earth in just over 6 seconds. The precise shape of its orbit, including relativistic effects like gravitational redshift and orbital precession, matches Einstein's equations exactly. Even the recent direct images of black holes from the Event Horizon Telescope show exactly what we'd expect from curved spacetime. The bright ring of hot gas orbiting around the black hole's shadow follows precise trajectories determined by the geometry of spacetime. The light from this hot gas gets bent and focused by the curved spacetime, creating the distinctive bright ring we see in the images. This means gravity doesn't need to escape from inside a black hole, because gravity isn't something that comes from inside in the first place. The black hole is the curvature. The gravitational effects are simply the geometry of space-time in that region. When we ask how gravity escapes a black hole, we're making the same mistake as asking how the shape of a bowl holds water. The bowl doesn't send out mysterious forces to grab the water. The water simply follows the curved surface that the bowl creates. Similarly, objects near a black hole simply follow the curved spacetime that the black hole is. But this raises another question. If the spacetime curvature around a black hole is just frozen geometry, where exactly does that curvature come from? How did it get there in the first place? And why does it persist even after the matter that created it has disappeared behind an event horizon? This geometric view of gravity explains so much about what we observe in the universe. When the Hubble Space Telescope captures images of gravitational lensing, showing distant galaxies stretched and magnified into perfect rings around massive clusters, we're seeing light following curved paths through warped space-time. The light isn't being pulled or deflected by a force. It's simply traveling in straight lines through curved space. When astronomers measure the orbits of stars around the supermassive black hole at the center of our galaxy, they find perfect agreement with Einstein's predictions. These stars aren't being yanked around by mysterious gravitational signals broadcast from inside the black hole. They're following geodesics, the straightest possible paths through the curved space-time geometry that exists around the black hole. Even the recent direct images of black holes from the Event Horizon Telescope show exactly what we'd expect from curved space-time. The bright ring of hot gas orbiting around the black hole's shadow follows precise trajectories determined by the geometry of space-time. No forces, no signals, just matter and energy, following the natural paths that curved spacetime provides. This is why physicists get excited about general relativity. It's not just a mathematical theory, it's a completely different way of understanding reality. Instead of thinking about objects pushing and pulling on each other across empty space, we realize that space itself is dynamic, curved, and responsive to the matter and energy within it. The mathematics of general relativity, Einstein's field equations, describe exactly how matter and energy curve spacetime, and how that curved spacetime guides the motion of matter and energy. It's a beautiful, self-consistent description of gravity that has passed every experimental test we've thrown at it for over a century. And here's the key insight for understanding black holes. The curvature of spacetime doesn't require ongoing communication between masses. It's not like electromagnetic fields, where moving charges constantly broadcast photons to create forces on other charges. Gravitational curvature is built into the very structure of spacetime itself. When we watch two black holes spiral toward each other and merge, releasing gravitational waves that we can detect billions of light years away, we're not seeing gravity escape from inside the event horizons. We're seeing the dynamic curvature of space-time itself rippling outward at the speed of light, carrying energy and information about the changing geometry of space and time. This brings us to a crucial realization about black holes and gravity. The question isn't how gravity gets out of a black hole. The question is, where does the curved space-time around a black hole actually come from? And how does it maintain its shape over billions of years without any ongoing input from the matter that originally created it. If gravity is just curved space-time, then where exactly does that curvature come from around a black hole? This question gets to the heart of one of the most beautiful aspects of Einstein's theory. The answer reveals why black holes don't need to send gravitational signals from their interiors, because their gravitational influence was locked into the fabric of space-time long before the event horizon ever formed. To understand this, we need to watch what happens when a massive star collapses into a black hole. Imagine a star 20 times more massive than our Sun reaching the end of its life. For millions of years, this star has been fighting a cosmic battle between the outward pressure of nuclear fusion and the inward pull of its own gravity. But when the nuclear fuel runs out, gravity wins decisively. The collapse happens incredibly fast. In less than a second, the star's core, which was once the size of Earth, shrinks to a point smaller than a city. The outer layers crash inward at speeds approaching a significant fraction of the speed of light. From the outside, we would see the star's surface growing dimmer and redder as it approaches what will become the event horizon. But here's the crucial point that solves our paradox. Throughout this entire collapse, the curvature of space-time outside the collapsing star remains virtually unchanged. The star's mass was already curving space-time before the collapse began, and that curvature persists as the collapse continues. Think of it this way. Before the collapse, the star had 20 solar masses worth of material spread out over a radius of perhaps 10 million kilometers. This mass curved space-time in a specific pattern. As the star collapses, that same 20 solar masses gets compressed into a smaller and smaller volume. But the total amount of mass-curving space-time remains the same. From the perspective of someone orbiting far from the star, the gravitational effects barely change at all during the collapse. A planet orbiting at the distance of Earth's orbit around the Sun would continue in exactly the same orbit, whether the central star was a normal star, a white dwarf, a neutron star, or a black hole, as long as the total mass remained the same. This is one of the most counterintuitive aspects of black hole formation. The dramatic event of stellar collapse, one of the most violent processes in the universe, leaves the external gravitational field almost completely unchanged. The space-time curvature that existed before the collapse becomes frozen into the geometry around the newly formed black hole. But what exactly do we mean by frozen? This is where the physics becomes truly fascinating. In Einstein's theory, the curvature of space-time is determined by something called the stress-energy tensor, which includes not just mass, but also energy, pressure, and momentum. As the star collapses, this stress-energy distribution changes dramatically, but only inside the shrinking boundary of the collapsing matter. The key insight is that changes in the stress-energy tensor can only affect space-time curvature at the speed of light. Information about the changing mass distribution inside the collapsing star travels outward as gravitational waves, ripples in space-time that carry energy and momentum. But these waves are created by the accelerating motion of the collapsing matter, not by any signal trying to escape from inside an event horizon. By the time the event horizon forms, the external space-time geometry has already been established by the gravitational waves that propagated outward during the collapse. The curvature pattern that we observe around a black hole is essentially the final snapshot of the gravitational field as it existed just before the event horizon formed. This is why we say the gravitational field around a black hole is static. It's not that nothing ever changes, but rather that the pattern of curvature outside the event horizon becomes a permanent feature of space-time geometry. The black hole doesn't need to send out ongoing signals to maintain its gravitational influence, because that influence is built into the structure of space and time itself. To make this more concrete, consider what happens to light rays and particle trajectories near the forming black hole. As the star collapses, light rays that were previously able to escape from the star's surface find it increasingly difficult to climb out of the deepening gravitational well. The escape velocity at the star's surface approaches the speed of light. At the moment the event horizon forms, light rays emitted from the surface become trapped on geodesics that never quite escape to infinity. They hover at the event horizon, neither falling in nor escaping out. From the perspective of a distant observer, these light rays appear to freeze at the horizon, growing dimmer and redder as their wavelengths stretch toward infinity. This gives us a beautiful picture of how the gravitational field becomes frozen. The last light rays to escape the collapsing star carry with them information about the mass and energy distribution just before the horizon formed. After that, no new information can escape, but the space-time curvature established by those final escaping signals remains permanently embedded in the geometry. The mathematics of this process is described by something called Birkhoff's theorem, which states that the space-time outside any spherically symmetric mass distribution is completely determined by the total mass, regardless of how that mass is distributed internally. Whether the mass is spread out as a normal star, compressed into a neutron star, or collapsed into a black hole, the external geometry remains the same. This theorem explains why the gravitational field around a black hole appears to remember properties of the original star, like its total mass, even after the star has disappeared behind the event horizon. The black hole isn't broadcasting this information from its interior. Instead, this information was stamped into the external space-time geometry during the collapse process and remains there permanently. But Birkhoff's theorem applies only to perfectly spherical mass distributions. Real stars aren't perfect spheres. They rotate, they have magnetic fields, and they lose mass through stellar winds. So what happens to this additional complexity when the star collapses into a black hole? The answer involves something called the no-hair theorem, which states that black holes can be completely characterized by just three properties: mass, electric charge, and angular momentum, or spin. Any other details about the original star, its chemical composition, its magnetic field strength, its surface temperature, all of this information is either radiated away during the collapse or falls behind the event horizon, where it can no longer influence the outside universe. The process by which a black hole loses all properties except mass, charge, and spin is sometimes called gravitational wave emission. As the collapsing star settles into its final black hole configuration, any asymmetries or irregular motions generate gravitational waves that carry away energy and angular momentum. The black hole rings like a struck bell, emitting gravitational waves at characteristic frequencies that depend only on its mass and spin. These ringing gravitational waves, called quasi-normal modes, are one of the most remarkable predictions of general relativity. They represent the black hole's space-time geometry, settling into its final stable configuration. The waves propagate outward at the speed of light, carrying away any information about the detailed structure of the original star and leaving behind only the simple, elegant geometry of a spinning black hole. This settling process typically takes only a few milliseconds for a stellar mass black hole. After that, the external spacetime reaches what physicists call a stationary state. The curvature pattern becomes fixed and unchanging, requiring no ongoing input from the black hole's interior to maintain itself. The resulting geometry, described mathematically by the Kerr metric for spinning black holes, has a remarkable property. Every aspect of the external gravitational field, from the way light rays bend around the black hole to the precession of orbital planes, is completely determined by just the black hole's mass and spin. No information about the black hole's interior is needed to predict these external effects. This is fundamentally different from other types of fields in physics. Electromagnetic fields, for example, require ongoing currents and charges to maintain themselves, If you turn off the current in a wire, the magnetic field disappears. But gravitational fields, once established, become part of the permanent architecture of space-time. This is fundamentally different from other types of fields in physics. Electromagnetic fields, for example, require ongoing currents and charges to maintain themselves. If you turn off the current in a wire, the magnetic field disappears almost immediately. The field lines collapse and the magnetic influence vanishes. But gravitational fields, once established in the fabric of space-time, become part of the permanent architecture of the universe. Consider what this means for our understanding of black holes. When we observe the supermassive black hole at the center of the Milky Way galaxy, we're not seeing gravitational signals being broadcast from inside the event horizon. We're seeing the permanent distortion in space-time that was created billions of years ago when that black hole first formed, possibly from the collapse of massive primordial stars or from the gradual accretion of matter in the early universe. The gravitational influence of Sagittarius A star, our galaxy's central black hole, extends across thousands of light years. It shepherds the orbits of billions of stars, influences the structure of spiral arms, and affects the dynamics of gas clouds throughout the galactic center. But this vast gravitational reach doesn't require any ongoing communication from the black hole's interior. It's simply the shape that space-time has in that region. This frozen field concept also explains why black holes can exist for virtually forever without losing their gravitational influence. Unlike other physical systems that require energy input to maintain their effects, a black hole's gravitational field is energetically neutral. It doesn't cost any energy to maintain the curvature of space-time, just as it doesn't cost energy for a mountain to continue being tall or for a valley to continue being deep. The implications of this go far beyond just understanding black holes. It reveals something profound about the nature of space-time itself. Space and time aren't just a passive backdrop for physics. They're dynamical entities that can store information and maintain structure over cosmic timescales. When astronomers study ancient black holes that formed in the early universe, just a few 100 million years after the Big Bang, they're seeing gravitational fossils. The space-time curvature around these primordial black holes preserves information about the mass and spin of whatever collapsed to create them billions of years ago, even though the original matter has long since disappeared behind the event horizon. This preservation of information in space-time geometry has practical consequences for modern astronomy. When we detect gravitational waves from merging black holes, we can determine not just their current masses and spins, but also information about their formation histories. The gravitational wave signals encode details about how these black holes formed, whether they came from stellar collapse or from earlier mergers, and how they evolved over cosmic time. The recent detections by LIGO and Virgo have revealed a universe filled with merging black holes, each one preserving the fossilized imprint of ancient stellar collapses in its gravitational field. When two black holes spiral toward each other and eventually merge, their individual frozen gravitational fields combine to create a new, more complex pattern of space-time curvature. During the final moments of a black hole merger, the space-time geometry becomes highly dynamical. The two individual black holes, each with their own static gravitational fields, create a rapidly changing pattern of curvature as they orbit each other at incredible speeds. This dynamical curvature generates powerful gravitational waves that carry energy away from the system. But even during these violent mergers, the basic principle holds. The gravitational effects we observe arise from the curvature of space-time outside the event horizons of the merging black holes. No information or influence escapes from inside the black holes themselves. The merger is entirely a consequence of the interaction between the external gravitational fields that were frozen into place when each black hole originally formed. After the merger completes, the newly formed black hole goes through its own settling process, emitting gravitational waves as its space-time geometry adjusts to a new static configuration. The final result is a single black hole with a mass slightly less than the sum of the two original black holes, the missing mass having been radiated away as gravitational wave energy during the merger process. This entire sequence, from the original stellar collapses that created the individual black holes, through their billion-year journey toward each other, to their final merger and settling, can be understood entirely in terms of space-time geometry. At no point does any information or influence need to escape from inside a black hole. The entire cosmic drama plays out in the curved space-time outside the event horizons. The mathematical description of this process involves solving Einstein's field equations in their full, non-linear glory. Unlike the relatively simple case of a single static black hole, merging black holes require numerical relativity, computer simulations that solve the field equations by dividing space-time into tiny cells and calculating how the curvature in each cell evolves over time. These simulations have revealed the incredible richness of black hole physics. They show how two initially circular orbits gradually become elliptical as gravitational wave emission removes energy from the system. They demonstrate how the black holes begin to precess, their spins tumbling like cosmic tops as they spiral closer together. They reveal the moment when the event horizons merge, creating a single, highly distorted black hole that oscillates and rings as it settles into its final configuration. All of this complexity emerges from the simple principle that mass and energy curve space-time, and curved space-time guides the motion of mass and energy. The gravitational influence of black holes never needs to escape from their interiors because it was never inside to begin with. It's written into the very geometry of space and time. So when we ask how gravity escapes from a black hole, we're asking the wrong question. Gravity doesn't escape because it was never inside to begin with. The gravitational influence we observe around black holes is the fossilized remnant of the space-time curvature that existed during the star's collapse, now frozen into the eternal geometry of the black hole's exterior. We've established that the gravitational field around a black hole is frozen into space-time geometry. But this raises a new question. What happens when black holes move or when their properties change? If two black holes are spiraling toward each other, or if matter falls into a black hole and increases its mass, how does the rest of the universe know about these changes? The answer reveals another beautiful aspect of Einstein's theory. Gravity can indeed change, but changes in gravitational fields propagate through space-time at exactly the speed of light, just like changes in electromagnetic fields. These propagating changes are gravitational waves, ripples in the fabric of space-time itself that carry information about accelerating masses across the cosmos. To understand how this works, we need to think more carefully about what we mean when we say gravitational fields are static. For a single isolated black hole sitting alone in empty space, the field really is completely static. The space-time curvature extends outward in a perfect, unchanging pattern that remains the same for all eternity. But real black holes don't exist in perfect isolation. They move through space, they accrete matter, and they interact with other massive objects. When a black hole accelerates or when its mass changes, these alterations in the stress-energy distribution create ripples in space-time that propagate outward at the speed of light. But here's the crucial point that resolves our paradox. These gravitational waves arise from changes in the space-time curvature outside the event horizon, not from signals trying to escape from inside the black hole. Consider what happens when two black holes orbit each other. Each black hole sits at the center of its own static gravitational field, but as they move in their orbital dance, the combined gravitational field of the system becomes time-dependent. The total pattern of space-time curvature changes as the black holes revolve around their common center of mass. From the perspective of a distant observer, this looks like two regions of curved space-time rotating around each other. As they spin, They create a time-varying pattern of gravitational field that propagates outward as gravitational waves. It's analogous to what happens when you shake two magnets near each other. The changing electromagnetic field pattern creates electromagnetic waves that carry energy away from the system. But there's a crucial difference between electromagnetic and gravitational radiation. Electromagnetic waves are created by accelerating electric charges, and those charges can be point-like particles. Gravitational waves, however, are created by accelerating masses, and in general relativity, there's no such thing as a point mass that creates gravitational waves efficiently. This is because of something called the equivalence principle, which states that gravity and acceleration are locally indistinguishable. A single point mass moving at constant velocity creates no gravitational waves at all, just a static field pattern that moves through space. To generate significant gravitational radiation, you need accelerating masses arranged in specific patterns that create what physicists call time-varying quadrupole moments. The most efficient way to create strong gravitational waves is to have two massive objects orbiting each other, like a binary system of neutron stars or black holes. As they orbit, their combined mass distribution creates a rotating pattern of space-time curvature that spirals outward as gravitational waves. These waves carry energy and angular momentum away from the system, causing the orbital separation to shrink and the orbital frequency to increase. The objects spiral closer together in an accelerating dance that eventually leads to a dramatic merger. This process, called inspiraling, can take billions of years for widely separated objects, but the final few seconds involve incredibly rapid changes. The first direct detection of gravitational waves, announced in February 2016, came from exactly such a system. The LIGO detectors measured the space-time ripples created by two black holes, each about 30 times the mass of our Sun, in their final moments before merger. The signal, designated GW150914, showed the characteristic chirp pattern of two objects spiraling together at ever-increasing speed. What's remarkable about this detection is how precisely it matched the predictions of general relativity. The gravitational wave signal encoded detailed information about the masses and spins of the two black holes, their orbital dynamics, and even the properties of the final merged black hole. Every aspect of the signal could be explained by the curvature dynamics of space-time outside the black hole event horizons. The waves detected by LIGO originated from a cosmic collision that happened over 1 billion years ago, when the universe was significantly younger and smaller. The gravitational waves traveled across this vast distance, carrying information about the merger with almost perfect fidelity. Along the way, they passed through galaxies, dark matter halos, and vast regions of nearly empty space, but the space-time ripples preserved their message across cosmic time. This gives us profound insight into the nature of gravitational information. Unlike electromagnetic signals, which can be absorbed or scattered by intervening matter, gravitational waves interact so weakly with normal matter that they travel through the universe almost completely unimpeded. They provide a direct view into the most violent events in the cosmos, events that would be completely invisible to ordinary telescopes. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, each one providing new insights into the population of black holes in the universe. Some mergers involve black holes with masses we expected from stellar evolution theory, but others have revealed black holes with masses that challenge our understanding of how such objects form. One particularly intriguing detection, GW190521, appeared to involve the merger of two black holes with very different masses, one about 90 times the mass of our Sun, and the other about 30 solar masses. The larger black hole was spinning rapidly, nearly at the maximum rate allowed by general relativity. The gravitational wave signal from this merger carried information about both objects across more than 5 billion light-years of space. These detections have opened an entirely new window on the universe, one that reveals cosmic phenomena that were previously hidden from view. Merging black holes produce no light, no radio waves, no X-rays, and no particles that we can detect directly. The only way we know they exist is through their gravitational influence, and the only way we can study their mergers is through gravitational waves. But gravitational waves don't just come from black hole mergers. They're also produced when neutron stars collide, when massive stars collapse asymmetrically, and potentially from exotic sources like cosmic strings or phase transitions in the early universe. Each type of source creates gravitational waves with characteristic signatures that encode information about the underlying physics. The detection of gravitational waves from merging neutron stars, designated GW 170817, provided a particularly dramatic demonstration of how gravity carries information across the cosmos. Unlike black hole mergers, which produce only gravitational waves, neutron star mergers also create spectacular electromagnetic displays called kilonovae. On August 17, 2017, LIGO and Virgo detected the gravitational wave signal from two neutron stars spiraling together about 130 million light-years away. Within seconds, gamma-ray telescopes detected a short gamma-ray burst from the same direction. Over the following days and weeks, optical and infrared telescopes watched as the kilonova brightened and faded, powered by the radioactive decay of heavy elements created in the merger. This multi-messenger observation, combining gravitational waves with electromagnetic signals, provided unprecedented insights into neutron star physics, the origin of heavy elements, and even the expansion rate of the universe. The gravitational waves arrived at Earth about 2 seconds before the gamma rays, consistent with the expectation that both types of radiation travel at the speed of light through the vacuum of space. The slight time difference between the gravitational and electromagnetic signals placed incredibly stringent limits on any possible difference between the speed of gravitational waves and the speed of light. The measurements showed that these speeds are identical to within 1 part in 10 to the 15th power, confirming one of the key predictions of general relativity with extraordinary precision. This observation also demonstrated how gravitational waves can provide information that's impossible to obtain any other way. The gravitational wave signal encoded the masses and spins of the two neutron stars before merger, information that would be extremely difficult to determine from electromagnetic observations alone. It also provided a direct measurement of the distance to the merger, independent of the cosmic distance ladder used in traditional astronomy. But perhaps the most profound implication of gravitational wave astronomy is what it tells us about the fundamental nature of space-time. Every gravitational wave detection confirms that space and time really do behave as Einstein predicted, responding dynamically to the presence of matter and energy and carrying information about that matter and energy across cosmic distances. The waves we detect today originated from the most extreme environments in the universe, regions where space-time curvature reaches its limits, and where the full nonlinear character of Einstein's equations becomes manifest. Near merging black holes, space-time itself becomes a turbulent, churning medium, with curvature gradients so steep that they generate powerful gravitational radiation. Yet even in these extreme conditions, no information ever escapes from inside the black hole event horizons. The gravitational waves that LIGO detects arise entirely from the dynamics of curved space-time outside the black holes. The merging process is a dance of external geometries, a cosmic ballet performed on the stage of space-time itself. This brings us back to our original question, with a clearer answer. Gravity doesn't escape from black holes, but gravity can certainly change, and those changes propagate through the universe at the speed of light as gravitational waves. When we detect these waves, we're not receiving signals from inside black holes. Instead, we're observing the dynamic evolution of space-time curvature in the regions outside the event horizons, where the fundamental physics of general relativity plays out on the grandest possible scale. Now that we understand how gravitational changes propagate through space-time, we can address a more fundamental question. Do black holes actually have gravitational fields in the traditional sense? The answer is yes, but these fields are unlike anything else in physics. They're completely static, perfectly predictable, and they encode only the most basic properties of the black holes that create them. To understand what makes black hole gravitational fields so special, we need to examine what astronomers have learned from decades of observations. The most detailed studies come from watching stars orbit around the supermassive black hole at the center of our own galaxy, an object called Sagittarius, a star that contains over 4 million times the mass of our Sun. For more than 20 years, astronomers have tracked individual stars as they follow elliptical orbits around this invisible giant. Using some of the world's most powerful telescopes, equipped with adaptive optic systems that correct for atmospheric turbulence, they can measure stellar positions with incredible precision, accurate to within a few millionths of an arc-second. One star in particular, designated S2, has provided the most dramatic confirmation of black hole physics. This star follows a highly elliptical orbit that brings it within just 120 astronomical units of Sagittarius, a star, at its closest approach. That's only about 3 times the distance from our Sun to Pluto. Incredibly close when you consider that the black hole has 4 million times the Sun's mass. At its closest approach in May 2018, S2 reached a speed of over 7,600 kilometers per second, which is about 2.5% of the speed of light. At these extreme speeds, and in such a strong gravitational field, the predictions of general relativity differ significantly from those of Newton's theory. The observations of S2's orbit have confirmed multiple relativistic effects with remarkable precision. As the star approaches the black hole, its light becomes gravitationally redshifted, meaning the wavelengths stretch and the light appears redder than it would if the star were farther from the black hole. The amount of redshift matches Einstein's predictions exactly. The orbit itself also shows relativistic precession, meaning the ellipse slowly rotates in space with each orbit. This is similar to the precession of Mercury's orbit around the Sun, but much more pronounced because of the extreme gravitational field. The rate of precession observed for S2 matches the predictions of general relativity to within the measurement uncertainties. These observations tell us something profound about the gravitational field around Sagittarius A star. Despite being a black hole with an event horizon from which nothing can escape, its external gravitational influence behaves exactly as Einstein's equations predict for a massive object with specific values of mass and spin. The key insight is that the gravitational field we observe around Sagittarius A star is completely determined by just 2 numbers, its total mass and its angular momentum, or spin. Every other detail about whatever matter originally collapsed to form this black hole has been erased from the external field. This is a manifestation of what physicists call the no-hair theorem, which states that black holes can be characterized by only 3 properties: mass, electric charge, and spin. The no-hair theorem is one of the most remarkable results in theoretical physics. It tells us that no matter how complex the original matter distribution that collapsed to form a black hole, no matter what its chemical composition, magnetic field strength, or internal structure, the resulting black hole's external gravitational field depends only on these 3 simple parameters. For astrophysical black holes, the electric charge is expected to be essentially 0, because any significant charge would quickly attract oppositely charged particles from the surrounding environment and neutralize itself. This leaves only mass and spin as the relevant parameters for describing real black holes in the universe. The mass determines the overall strength of the gravitational field and the size of the event horizon. A black hole with the mass of our Sun would have an event horizon with a radius of about 3 kilometers. Sagittarius A star, with its 4 million solar masses, has an event horizon roughly the size of Mercury's orbit around the Sun. The spin determines how the gravitational field is distorted by the black hole's rotation. A spinning black hole drags space-time around with it in an effect called frame dragging, or the Lenz-Thirring effect. This causes the orbits of nearby objects to precess in the direction of the black hole's rotation, and it creates a region outside the event horizon called the ergosphere, where nothing can remain stationary relative to distant observers. The mathematical description of a spinning black hole's gravitational field is given by the Kerr metric, discovered by Roy Kerr in 1963. This solution to Einstein's field equations describes the space-time geometry around any rotating black hole, regardless of how that black hole formed or what it's made of internally. The Kerr metric has been tested to extraordinary precision through observations of stellar orbits, gravitational wave detections, and even the direct imaging of black hole shadows by the Event Horizon Telescope. Every test confirms that real black holes behave exactly as the Kerr solution predicts, with no deviations or anomalies that might suggest additional complexity in their gravitational fields. This universality is truly remarkable. It means that if you know just the mass and spin of any black hole anywhere in the universe, you can predict every aspect of its external gravitational influence. The way light rays bend around it, the orbits of nearby stars, the emission of gravitational waves during mergers, even the appearance of its shadow as seen by telescopes. All of these phenomena are completely determined by just two numbers. The static nature of black hole gravitational fields has profound implications for our understanding of information and causality. Unlike electromagnetic fields, which can carry detailed information about the charges and currents that create them, gravitational fields around black holes carry almost no information about their interiors. This creates what physicists call the information paradox. If you throw a library full of books into a black hole, all that information about the book's contents is lost to the outside universe. The black hole's mass increases slightly, and perhaps its spin changes a bit, but no other trace of the books remains in the external gravitational field. From the perspective of someone outside the black hole, it's as if the information in those books has been destroyed, which would violate one of the fundamental principles of quantum mechanics, that information must be conserved. This paradox remains one of the deepest unsolved problems in theoretical physics, touching on the relationship between gravity, quantum mechanics, and the nature of information itself. But for the purposes of understanding how black holes exert gravitational influence, the key point is that their fields are completely static and predictable. Once a black hole forms and settles into its final configuration, its external gravitational field becomes a permanent feature of space-time geometry that requires no ongoing input to maintain itself. This is fundamentally different from other physical systems. A radio transmitter must continuously emit electromagnetic waves to influence distant receivers. A chemical reaction must continuously consume reactants to maintain its effects. But a black hole's gravitational influence is built into the fabric of space-time itself, as permanent and unchanging as the geometry of space. The permanence of black hole gravitational fields has been confirmed through observations spanning decades. Sagittarius A star has maintained precisely the same gravitational influence on surrounding stars for the entire time we've been observing it. The masses and spins of black holes detected through gravitational waves match the values inferred from their final merged states, showing that their gravitational properties remain constant throughout the merger process. Even more remarkably, we can observe black holes that formed billions of years ago in the early universe. and their gravitational fields show no signs of decay or evolution. Ancient quasars, powered by supermassive black holes, continue to gravitationally lens background galaxies with precisely the strength we'd expect based on their estimated masses. This timeless quality of black hole gravitational fields reflects a deeper truth about the nature of space-time. The curvature patterns that we call gravitational fields aren't temporary disturbances that fade away over time. They're permanent modifications to the geometric structure of the universe, as enduring as the black holes that create them. The mathematical formalism that describes this permanence involves something called killing vectors, which represent the symmetries of space-time. For a static black hole like one described by the Schwarzschild metric, there's a time-like killing vector that reflects the time translation symmetry of the geometry. This means that the space-time looks exactly the same at any moment in time, confirming the static nature of the gravitational field. For rotating black holes described by the Kerr metric, there's both a time-like killing vector and a space-like killing vector associated with rotational symmetry. This means that the gravitational field pattern rotates with the black hole, but otherwise remains completely unchanged over time. These symmetries aren't just mathematical abstractions, they have real physical consequences. The existence of time-like killing vectors is directly related to energy conservation in the spacetime, while rotational killing vectors are related to angular momentum conservation. The static nature of black hole gravitational fields is thus connected to the most fundamental conservation laws in physics. Understanding the static character of black hole gravitational fields brings us closer to resolving our original paradox. The gravitational influence of a black hole doesn't need to escape from its interior, because that influence was established during the black hole's formation and has remained unchanged ever since. It's written into the permanent architecture of space-time, as fixed and eternal as the geometry of the universe itself. The event horizon is perhaps the most mysterious boundary in all of physics. It's the point of no return around a black hole, the invisible surface beyond which nothing, not matter, not energy, not even light itself, can ever escape back to the outside universe. Yet somehow, the gravitational influence of whatever lies beyond this boundary continues to affect the space around it. How is this possible? To understand the event horizon, we need to think carefully about what it actually represents. It's not a physical surface like the boundary of a star or planet. There's no material there, no solid barrier that blocks escaping objects. Instead, the event horizon is a purely geometric feature of space-time, defined by the paths that light rays can take in the curved geometry around a black hole. The concept becomes clearer when we consider the idea of escape velocity. On Earth, you need to throw an object upward at about 11 kilometers per second for it to escape our planet's gravitational pull and never fall back down. This escape velocity increases with the mass of the gravitating body and decreases with distance from its center. For a black hole, there's a critical radius called the Schwarzschild radius, where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing inside this radius can ever escape. This critical radius defines the event horizon, and its size depends only on the black hole's mass. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For Sagittarius A star, the supermassive black hole at our galaxy's center, it's about 12 million kilometers, roughly the size of Mercury's orbit. These distances seem small compared to the vast gravitational influence these objects exert, which extends across light years of space. The mathematical definition of the event horizon is even more subtle than the escape velocity picture suggests. It's actually defined as the boundary of the causal past of future infinity. This technical language means it's the set of all points from which light signals can never reach distant observers, no matter how long those observers wait. This definition reveals something profound about the nature of information and causality around black holes. Events that occur inside the event horizon are causally disconnected from the rest of the universe. They can't influence anything outside, and nothing outside can learn about them through any physical signal or interaction. But here's the crucial insight that resolves our gravitational paradox. The event horizon only prevents information from getting out after it crosses the boundary. The gravitational influence we observe around black holes was established before the event horizon formed, during the collapse process that created the black hole in the first place. To see how this works, imagine watching a massive star collapse from a safe distance. As the star's surface shrinks, it becomes harder and harder for light to escape from increasingly deep in the gravitational well. The wavelengths of escaping light stretch longer and longer, shifting toward the red end of the spectrum and eventually beyond into the infrared and radio bands. From your distant perspective, the collapsing star appears to slow down as it approaches the Schwarzschild radius. The light becomes redder and dimmer, but it never quite disappears. Instead, the image of the star's surface seems to freeze at the event horizon, glowing with an increasingly faint, red shifted light that fades exponentially over time. This frozen image carries with it the last information about the gravitational field that will ever escape from the collapsing matter. The space-time curvature pattern established by this final burst of information becomes permanently embedded in the geometry outside the event horizon. It's important to understand that this freezing effect is purely a consequence of how we observe the collapse from outside. From the perspective of someone falling with the collapsing matter, the event horizon is passed in a finite time, and the collapse continues normally until the matter reaches the central singularity. This difference in perspectives reveals one of the most mind-bending aspects of general relativity. There's no universal, absolute notion of simultaneity that everyone can agree on. Events that appear simultaneous to one observer may occur at different times according to another observer in a different state of motion or in a different gravitational field. The event horizon itself illustrates this relativity of simultaneity in an extreme way. To distant observers, matter never quite crosses the event horizon, but instead appears to freeze there forever. To infalling observers, the horizon is crossed in finite time, but they can never send signals back to tell outside observers about their experience. This observer dependence doesn't mean that event horizons are somehow illusory or that different observers disagree about the basic physics. Instead, it reflects the deep connection between gravity, space-time geometry, and the flow of information in the universe. From the standpoint of outside observers, who are the ones asking how gravity escapes from black holes, the relevant physics all occurs outside the event horizon. The gravitational field they observe is determined by the matter and energy distribution as it existed just before crossing the horizon, frozen into the space-time geometry by the last escaping light signals. The event horizon acts like a one-way membrane for information. Signals can cross from outside to inside, but never from inside to outside. This information barrier is what prevents us from learning anything about the interior of a black hole after it forms. But it doesn't prevent the exterior gravitational field from existing, because that field was established before the barrier formed. Modern physics has revealed that the event horizon has even stranger properties than Einstein originally realized. Quantum field theory predicts that the vacuum of space near an event horizon is actually filled with particle-antiparticle pairs that spontaneously appear and disappear on incredibly short timescales. Near the event horizon, something remarkable happens to these quantum fluctuations. Occasionally, one member of a particle-antiparticle pair falls across the horizon, while the other escapes to infinity. The escaping particle carries positive energy away from the black hole, while the particle that falls in must carry negative energy to preserve conservation laws. This process discovered by Stephen Hawking in 1974, means that black holes actually evaporate over time by emitting what's now called Hawking radiation. The radiation appears to come from just outside the event horizon, created by quantum effects in the curved spacetime around the black hole. Hawking radiation provides another example of how information and energy can emerge from the vicinity of a black hole without violating the prohibition against escape from inside the event horizon. The radiation is generated by quantum processes in the curved spacetime outside the horizon, not by any signal or influence from the black hole's interior. For stellar mass black holes, Hawking radiation is incredibly weak, with temperatures much colder than the cosmic microwave background. These black holes would take longer than 10 to the 67th power years to evaporate completely, far longer than the current age of the universe. But the principle is important because it shows that even the seemingly absolute barrier of the event horizon can be circumvented by quantum effects. The discovery of Hawking radiation also revealed new paradoxes about information and black holes. If black holes evaporate completely through Hawking radiation, what happens to the information that fell into them? Quantum mechanics says information must be conserved, but Hawking radiation appears to be completely thermal, carrying no information about what created the black hole. This information paradox has driven decades of research into the quantum nature of black holes and spacetime. Proposed solutions range from the idea that information is gradually encoded in subtle correlations in the Hawking radiation, to more radical suggestions that the interior of a black hole doesn't exist in the way we normally think about it. Some theories propose that the event horizon is replaced by a highly energetic firewall that destroys anything trying to cross it. Others suggest that the interior and exterior of a black hole are connected through quantum entanglement in ways that preserve information while maintaining the apparent barrier to communication. These quantum effects don't change the basic picture of black hole gravitational fields that we've developed. Whether or not information can eventually escape through Hawking radiation or other quantum processes, the classical gravitational influence of black holes is still determined by the space-time curvature outside the event horizon. The event horizon remains a boundary that prevents classical information from escaping, but it doesn't prevent the gravitational geometry established during black hole formation from continuing to influence the surrounding space-time. The curvature pattern exists outside the horizon, where it can interact with matter, bend light rays, and create all the gravitational effects we observe. Even in quantum theories of gravity, where the nature of event horizons may be more subtle than in classical general relativity, the basic principle holds. The gravitational influence of black holes arises from the curvature of space-time in regions that are causally connected to outside observers. This brings us to a deeper understanding of why nothing needs to escape from inside a black hole to explain its gravitational effects. The event horizon is a boundary in space-time that prevents information from crossing from inside to outside. But the gravitational field exists in the space-time outside this boundary, where it was established during the black hole's formation and where it continues to shape the geometry of space and time. The event horizon thus serves as the ultimate demonstration that gravity isn't something that emanates from mass like light from a lamp. Instead, it's the shape of space-time itself, a shape that can persist and influence the universe long after the matter that created it has passed beyond the point of causal contact with the outside world. The discovery of Hawking radiation opened up one of the most profound puzzles in modern physics, the black hole information paradox. This paradox sits at the intersection of quantum mechanics, general relativity, and our understanding of information itself. While it doesn't directly concern how gravity escapes from black holes, it reveals deep truths about the nature of information flow around event horizons that help us understand why gravitational influence doesn't require escape. To understand the information paradox, we need to appreciate how central the concept of information conservation is to quantum mechanics. In the quantum world, information about a system's state is never truly destroyed, only transformed or redistributed. When particles interact, their quantum states become entangled in ways that preserve all the original information, even though it may become scrambled and difficult to extract. This principle of information conservation, also called unitarity, is one of the fundamental pillars of quantum theory. It ensures that the laws of physics are reversible in principle, that if you could run the universe backward, all the quantum information would unscramble and return to its original state. Black holes appear to violate this principle in a dramatic way. When matter falls into a black hole, it carries quantum information about its internal state, its particle composition, its energy distribution, and countless other microscopic details. From the outside perspective, this information disappears behind the event horizon and becomes causally disconnected from the rest of the universe. If black holes were perfectly stable, this wouldn't necessarily create a paradox. The information would still exist, just in a region of space-time that's inaccessible to outside observers. But Hawking's discovery changed everything by showing that black holes actually evaporate over time through quantum radiation. Hawking radiation emerges from quantum fluctuations in the curved space-time just outside the event horizon. These fluctuations create particle-antiparticle pairs, with one member of each pair falling into the black hole while the other escapes to infinity. The escaping particles carry energy away from the black hole, causing it to gradually shrink and eventually disappear completely. The problem is that Hawking radiation appears to be completely thermal, meaning it carries no information about what fell into the black hole originally. It's like the radiation from a hot stove, characterized only by a temperature that depends on the black hole's mass. If this thermal radiation is all that escapes during the evaporation process, then the quantum information that fell into the black hole would be permanently destroyed when the black hole finally disappears. This creates a fundamental conflict between general relativity, which allows information to disappear behind event horizons, and quantum mechanics, which demands that information must always be conserved. The paradox has driven decades of research and has led to some of the most creative and controversial ideas in theoretical physics. One proposed resolution suggests that information is actually encoded in subtle correlations within the Hawking radiation, correlations so complex that they would be virtually impossible to detect or decode in practice. According to this view, the radiation only appears thermal because we don't have the capability to measure the incredibly delicate quantum correlations that carry the information. This idea requires that the Hawking radiation from a black hole becomes increasingly correlated with earlier radiation as the evaporation process continues. By the time the black hole has lost about half its mass, the emerging radiation would need to be maximally entangled with all the radiation that had been emitted previously. The transition point where this maximal entanglement begins is called the Page time, named after physicist Don Page, who calculated when it should occur. For a black hole with the mass of our Sun, the Page time would be about 10 to the 64th power years, an almost incomprehensibly long time compared to the current age of the universe. But measuring these correlations, even in principle, presents enormous challenges. The quantum information would be spread across all the Hawking radiation emitted throughout the black hole's entire evaporation history. Reconstructing the original information would require collecting and analyzing every single photon of Hawking radiation, then performing quantum computations of mind-boggling complexity. Another proposed resolution to the information paradox involves reconsidering the nature of the black hole interior itself. Some physicists suggest that the smooth space-time geometry that general relativity predicts inside black holes might be replaced by something much more exotic at the quantum level. One such proposal is the firewall hypothesis, which suggests that the event horizon is actually a region of incredibly high energy density that would instantly destroy anything trying to cross it. According to this idea, infalling matter never actually reaches the black hole's interior, but is instead incinerated at the horizon and converted into outgoing Hawking radiation. The firewall hypothesis resolves the information paradox by ensuring that no information ever truly enters the black hole interior. Instead, all the quantum information gets scrambled and re-encoded in the outgoing radiation at the moment of apparent horizon crossing. But this solution comes at the cost of violating the equivalence principle, which says that freely falling observers shouldn't experience anything special when crossing an event horizon. Even more radical proposals suggest that the interiors of black holes might not exist at all in the conventional sense. These ideas, inspired by the holographic principle and string theory, propose that all the physics of a black hole can be described entirely in terms of quantum information, processing on the event horizon surface. According to the holographic principle, the information content of any region of space can be encoded on its boundary surface, much like a hologram encodes three-dimensional information on a two-dimensional surface. For black holes, this means that everything we think of as happening in the interior might actually be a holographic projection of quantum processes occurring on the event horizon. These holographic ideas have led to some of the most mathematically sophisticated approaches to the information paradox. They suggest that black holes might be described by quantum systems with a finite number of degrees of freedom, proportional to the area of the event horizon rather than the volume of the interior. The mathematics involved in these approaches often requires advanced techniques from string theory, quantum field theory, and information theory. Researchers study simplified models of black holes in lower dimensional spacetimes, where the calculations become more tractable while still capturing the essential physics of the information paradox. One particularly influential approach involves studying black holes in a two-dimensional spacetime called ADS2, which stands for two-dimensional anti-de Sitter space. In this simplified setting, physicists have been able to construct exact solutions that appear to resolve the information paradox while preserving both general relativity and quantum mechanics. These toy models suggest that the resolution of the information paradox might involve quantum error correction, a process borrowed from quantum computing where information is protected from corruption by encoding it redundantly across multiple quantum systems. The idea is that quantum information falling into a black hole gets encoded across the entire surface of the event horizon in such a way that it can be recovered, even if parts of the encoding are lost. But regardless of which approach ultimately proves correct, all proposed solutions to the information paradox share a common feature. They locate the resolution in quantum processes that occur at or near the event horizon, not in any communication from the black hole's interior to the outside universe. This is crucial for understanding why the information paradox doesn't affect our resolution of the gravitational paradox. Even if quantum information can somehow escape from black holes through subtle correlations in Hawking radiation or through horizon-based holographic encoding, this doesn't mean that classical gravitational influence needs to escape from the interior. The gravitational field around a black hole is established by the spacetime curvature outside the event horizon, curvature that was created during the black hole's formation, and that persists as a geometric feature of spacetime. This classical gravitational influence doesn't carry detailed information about the black hole's interior, just the basic parameters of mass, charge, and spin that characterize the external geometry. Hawking radiation and other quantum effects near the event horizon might eventually carry away detailed quantum information about what fell into the black hole, but they don't carry the gravitational influence itself. That influence is built into the structure of spacetime and doesn't need to escape because it was never inside to begin with. The information paradox thus represents a separate puzzle from the gravitational paradox we're trying to understand. It concerns the fate of quantum information in curved spacetime, while the gravitational paradox concerns the nature of space-time curvature itself. Understanding this distinction helps clarify why black holes can have both strong gravitational influence and perfect information barriers. The gravitational influence arises from the geometry of space-time outside the event horizon, while the information barrier prevents detailed knowledge about the interior from reaching outside observers. This separation between geometry and information is one of the most profound insights to emerge from the study of black holes. It suggests that space-time itself is more fundamental than the matter and energy that curve it, and that geometric relationships can persist even when the information that created them becomes inaccessible. The ongoing research into the information paradox continues to deepen our understanding of these issues. New mathematical tools from quantum information theory, holography, and string theory are providing fresh perspectives on how information and geometry interact in the most extreme environments in the universe. But for our purposes, the key lesson is that the information paradox doesn't undermine our resolution of the gravitational paradox. Both problems find their solutions in understanding the subtle relationship between the interior and exterior of black holes, and both point toward the fundamental role of space-time geometry in determining how the universe works at its deepest level. As our understanding of black holes has deepened, physicists have proposed increasingly exotic theories that challenge our basic assumptions about space-time, causality, and the nature of reality itself. Some of these ideas suggest radical departures from Einstein's general relativity, while others propose that space and time themselves might be emergent properties of more fundamental quantum systems. But do any of these exotic theories actually allow gravity to escape from inside black holes? The short answer is no. Even the most speculative theories in modern physics respect the basic causal structure that prevents information from traveling faster than light. But exploring these exotic ideas reveals fascinating possibilities for how the universe might work at its deepest level, and they provide important context for understanding why our resolution of the gravitational paradox remains robust. One of the most intriguing exotic theories involves the possibility of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes altogether. The idea was first explored mathematically by Einstein and Nathan Rosen in 1935, leading to what are sometimes called Einstein-Rosen bridges. A wormhole would consist of two mouths connected by a throat that passes through higher dimensional space. In principle, you could enter one mouth and emerge from the other, potentially traveling vast distances instantaneously, or even journeying backward in time. Some scientists have speculated that the interiors of black holes might be connected to the exteriors through such wormhole geometries. The most famous modern version of this idea is the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. ER refers to Einstein-Rosen bridges, while EPR refers to the Einstein-Podolsky-Rosen paradox of quantum entanglement. The conjecture suggests that quantum entanglement between particles might be geometrically realized as tiny wormholes connecting the particles through higher dimensional space. If this conjecture is correct, then the quantum entanglement between particles inside and outside a black hole might correspond to microscopic wormholes that connect the interior and exterior regions. This could potentially allow information to flow between the interior and exterior without violating the causal structure of the event horizon. But even if such wormholes exist, they wouldn't allow gravitational influence to escape from inside black holes in the conventional sense. The gravitational effects we observe around black holes arise from the space-time curvature outside the event horizon, not from any communication through wormhole connections. Moreover, traversable wormholes, the kind that would allow information or influence to pass through them, require exotic matter with negative energy density to keep them open. Such matter has never been observed in nature, and quantum field theory suggests that it might be impossible to create or maintain in macroscopic quantities. Most wormhole solutions in general relativity are inherently unstable, collapsing to black holes or expanding to infinity faster than light could traverse them. Even if microscopic wormholes exist at the quantum level, they would likely be far too small and short-lived to carry significant gravitational influence. Another class of exotic theories involves modified gravity, attempts to alter Einstein's equations to explain dark matter and dark energy without invoking invisible forms of matter and energy. Some of these theories, such as modified Newtonian dynamics or MOND, suggest that gravity behaves differently at very low accelerations or over cosmic distances. Other modified gravity theories, like F of R gravity or scalar tensor theories, introduce additional fields or modify the mathematical structure of space-time itself. These theories make different predictions for strong field environments, like the vicinity of black holes, potentially allowing for new phenomena that don't exist in standard general relativity. But even in modified gravity theories, the basic causal structure of space-time is preserved. Event horizons still prevent information from escaping, and gravitational influence still propagates at the speed of light. The modifications typically affect the detailed form of the gravitational field equations, not the fundamental principles of causality and information flow. Some of the most radical proposals come from string theory, the attempt to unify general relativity with quantum mechanics by describing fundamental particles as tiny vibrating strings rather than point-like objects. String theory suggests that our familiar three-dimensional space might actually be embedded in a higher dimensional space with up to 11 dimensions. In string theory, black holes can be modeled as collections of strings and brains, higher dimensional objects that extend through the extra dimensions. These models have led to new insights into black hole thermodynamics and have provided some of the most promising approaches to resolving the information paradox. One particularly influential idea from string theory is the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence establishes a mathematical equivalence between certain types of gravitational theories in curved spacetime and quantum field theories defined on the boundary of that spacetime. The ADS-CFT correspondence suggests that the physics inside a region of spacetime, including the interior of black holes, might be completely equivalent to quantum field theory processes occurring on the boundary of that region. This holographic relationship implies that three-dimensional gravity might emerge from two-dimensional quantum field theory, much like a hologram creates the illusion of three-dimensional images from information stored on a two-dimensional surface. If the ADS-CFT correspondence applies to real black holes, it would mean that everything happening inside a black hole is perfectly reflected in quantum processes occurring on or near the event horizon. The interior would still exist as a geometric region of space-time, but all its physics would be encoded in the boundary theory. This holographic picture provides a new perspective on how information flows around black holes. Instead of information being trapped inside the event horizon, it would be encoded in the quantum degrees of freedom on the horizon surface. This could potentially resolve the information paradox while maintaining the causal structure that prevents signals from escaping the interior. But even in the holographic picture, gravitational influence doesn't escape from inside black holes. The correspondence shows that interior physics is equivalent to boundary physics, not that interior influences can propagate to the exterior faster than light. The gravitational field around a black hole would still be determined by the space-time curvature outside the event horizon. Loop quantum gravity represents another radical approach to unifying general relativity with quantum mechanics. Instead of treating space-time as a smooth continuum, Loop quantum gravity suggests that space and time themselves are quantized at the smallest scales, made up of discrete units connected in a network-like pattern. In loop quantum gravity, the singularities that general relativity predicts at the centers of black holes are replaced by quantum bounces, regions where the curvature reaches a maximum value and then decreases again. This could potentially create pathways for information to escape from black holes through quantum tunneling effects. Some loop quantum gravity models suggest that black holes might eventually evolve into white holes, hypothetical objects that spew matter and energy outward instead of absorbing it. The transition from black hole to white hole would occur through quantum effects in the deep interior, potentially allowing information that fell into the black hole to eventually escape. But even these exotic scenarios don't involve gravitational influence escaping from inside black holes. The quantum bounce effects predicted by loop quantum gravity occur in the deep interior, far inside the event horizon, where they can't influence the external space-time geometry. The gravitational field outside the black hole would remain unchanged throughout any interior quantum evolution. Causal set theory offers yet another perspective on the fundamental nature of space-time. This approach suggests that space-time is made up of discrete events connected by causal relationships, rather than being a continuous manifold as Einstein envisioned. In causal set theory, the smooth geometry of general relativity emerges as an approximation when you consider large numbers of discrete events. The discrete structure of causal sets could potentially allow for new types of quantum effects that don't exist in continuous spacetime. Some researchers have speculated that information might be able to propagate through causal set networks in ways that wouldn't be possible in smooth spacetime geometries. But causal set theory is built on the principle that causal relationships are fundamental, meaning that the basic rule against faster-than-light communication is even more strictly enforced than in general relativity. Information can only flow along the causal links that connect discrete events, and these links still respect the light speed limit. Even more speculative ideas involve the possibility that our entire universe might be a holographic projection from information processing occurring on a distant boundary. According to some interpretations of the holographic principle, the three-dimensional reality we experience might be an emergent property of quantum computations happening on a two-dimensional surface at the edge of our cosmic horizon. If this cosmic holography is real, then black holes within our universe would themselves be holographic projections of boundary processes. Their gravitational influence would arise from the holographic encoding of mass and energy information on the cosmic boundary, not from any matter existing in our three-dimensional space. But even in such radical scenarios, the holographic black holes would still obey the same causal constraints as real black holes. Their event horizons would still prevent information from escaping, and their gravitational influence would still be determined by the space-time curvature outside those horizons. The common thread running through all these exotic theories is that they preserve the fundamental causal structure of space-time, even as they propose radical changes to our understanding of what space-time actually is. Whether space-time is smooth or discrete, whether it's fundamental or emergent, whether it's three-dimensional or holographically encoded, the basic principle remains that information cannot propagate faster than light. This causal constraint is what prevents gravitational influence from escaping the interiors of black holes, regardless of what exotic physics might be occurring inside them. The gravitational field we observe around black holes arises from the curvature of space-time outside the event horizon, curvature that was established during the black hole's formation, and that persists as a geometric feature of whatever underlying reality gives rise to our observed space-time. The exploration of exotic theories thus reinforces rather than undermines our resolution of the gravitational paradox. Even in the most speculative scenarios, gravity doesn't need to escape from inside black holes because gravitational influence is a property of space-time geometry, not a signal that needs to be transmitted from one location to another. The theoretical arguments we've explored are compelling, but science ultimately depends on observation and experiment. What do we actually see when we look at real black holes in the universe? Do our observations confirm that gravitational influence arises from space-time curvature outside the event horizon, or do they reveal something more mysterious? The answer comes from some of the most remarkable astronomical observations in human history. Over the past few decades, advances in telescope technology, detector sensitivity, and data analysis have given us unprecedented views of black holes and their gravitational effects. Every observation confirms the picture we've developed. Gravitational influence extends far beyond black holes, but it arises entirely from the curved space-time outside their event horizons. The most detailed observations come from studying the supermassive black hole at the center of our own galaxy. Sagittarius A star, as astronomers call it, has been under continuous surveillance for over 30 years. Using some of the world's most powerful telescopes, equipped with adaptive optic systems that correct for atmospheric turbulence, astronomers can track individual stars as they orbit this invisible giant. The precision of these observations is almost beyond belief. Astronomers can measure stellar positions accurate to within a few millionths of an arc-second, equivalent to seeing a coin on the moon from Earth. They can detect changes in stellar velocities as small as a few kilometers per second, and they can measure the stretching and compression of light wavelengths caused by gravitational fields. One star in particular, designated S2, has provided the most stringent test of black hole physics ever achieved. This star follows a highly elliptical orbit that brings it within about 120 astronomical units of Sagittarius A star at its closest approach. That's only about 4 times the distance from our Sun to Neptune. Incredibly close, considering that the black hole contains over 4 million solar masses. During its closest approach in May 2018, S2 reached a velocity of about 25 million kilometers per hour, roughly 2.5% of the speed of light. At these extreme speeds, and in such a strong gravitational field, the predictions of general relativity differ dramatically from those of Newton's theory. The observations revealed multiple relativistic effects with stunning precision. As S2 approached the black hole, its light became gravitationally redshifted, with wavelengths stretching as photons climbed out of the deep gravitational well. The amount of redshift exactly matched Einstein's predictions, confirming that the gravitational field around Sagittarius A star behaves precisely as general relativity predicts. The orbit itself also showed clear signs of relativistic precession. Instead of following the same elliptical path each orbit, the ellipse slowly rotates in space, with its closest approach point advancing by a small amount each time around. This precession occurs because space-time near the black hole is curved in ways that Newton's theory cannot account for. The measured precession rate for S2's orbit is about 12 arc-minutes per orbit, roughly the size of a small crater on the Moon as seen from Earth. This tiny effect matches the predictions of the Schwarzschild metric, the solution to Einstein's equations for the space-time around a non-rotating black hole. These observations provide direct confirmation that the gravitational field around Sagittarius A star is determined entirely by the space-time curvature outside its event horizon. There's no need for any gravitational influence to escape from the black hole's interior to explain what we observe. The external curvature pattern, characterized by the black hole's mass, accounts for every detail of stellar motion in the galactic center. Even more remarkable are the observations of gravitational lensing around black holes and other massive objects. When light passes near a massive object, its path bends due to the curvature of space-time. This gravitational lensing can magnify, distort, and multiply the images of background sources, creating some of the most beautiful and scientifically valuable observations in astronomy. The Hubble Space Telescope has captured hundreds of images showing gravitational lensing by galaxy clusters, massive collections of galaxies and dark matter that can contain the equivalent of thousands of trillions of suns. When distant galaxies lie behind these clusters, their light gets bent and focused by the cluster's gravitational field, often creating perfect rings or multiple images of the same galaxy. These lensing observations allow astronomers to map the distribution of matter in the lensing clusters with incredible precision. They can determine not only the total mass of the cluster, but also how that mass is distributed in three-dimensional space. The results consistently match the predictions of general relativity for how mass curves space-time. Some of the most dramatic lensing effects occur around supermassive black holes in the centers of distant galaxies. These black holes can act as gravitational telescopes, magnifying background sources and allowing us to see objects that would otherwise be too faint to detect. The magnification patterns depend sensitively on the mass and spin of the lensing black hole, providing another way to test our understanding of black hole gravitational fields. The Event Horizon Telescope has provided perhaps the most direct view of space-time curvature around black holes. This globe-spanning array of radio telescopes works together to create images with resolution sharp enough to see the shadow cast by a black hole's event horizon. The first target was the supermassive black hole at the center of the galaxy M87, located about 54 million light-years from Earth. This black hole, designated M87 star, contains about 6.5 billion solar masses, making it one of the most massive black holes known. The Event Horizon Telescope image shows a bright ring of hot gas orbiting around a dark central shadow. The shadow corresponds to the black hole's event horizon, the boundary from which no light can escape. The bright ring is created by hot plasma spiraling around the black hole at nearly the speed of light, heated to billions of degrees by friction and magnetic fields. The shape and size of the shadow exactly match the predictions of general relativity for a black hole with M87 star's estimated mass and spin. The asymmetry in the bright ring, brighter on one side than the other, results from relativistic beaming effects as the plasma moves at high speeds around the curved spacetime. These images provide visual confirmation that black holes really do curve spacetime in the way Einstein predicted. The light from the hot plasma follows geodesics, the straightest possible paths through the curved geometry around the black hole. No mysterious forces are needed to explain the bending of light rays, just the natural consequence of photons traveling through curved spacetime. The Event Horizon Telescope has also imaged Sagittarius A star, our own galaxy's central black hole. Despite being much closer than M87 star, Sagittarius A star proved more challenging to image because it's much smaller and the hot gas around it changes much more rapidly. The resulting image shows a similar bright ring and dark shadow structure, confirming that both black holes behave according to the same physical principles. The consistency between these observations and general relativity's predictions provides powerful evidence that our understanding of black hole gravitational fields is correct. Perhaps the most revolutionary observations have come from the detection of gravitational waves by LIGO Virgo and other gravitational wave observatories. These detections provide a completely new way of studying black holes, one that reveals information about their masses, spins, and merger dynamics that would be impossible to obtain through electromagnetic observations. The first detection, GW150914, came from the merger of two black holes with masses of about 29 and 36 solar masses respectively. The gravitational waves were generated as these black holes spiraled around each other in their final moments before collision, creating ripples in space-time that propagated across over 1 billion light-years to reach Earth. The detected signal showed the characteristic chirp pattern predicted by general relativity, with the frequency and amplitude increasing as the black holes approached each other. The final moments of the merger when the two event horizons touched and merged into a single black hole, created the strongest gravitational wave signal ever observed. Every aspect of this detection matched the predictions of numerical relativity simulations based on Einstein's field equations. The masses and spins of the individual black holes, the dynamics of their orbital evolution, and the properties of the final merged black hole all agreed with theoretical expectations to within measurement uncertainties. Since that first detection, LIGO and Virgo have observed dozens of black hole mergers, each one providing new insights into the population of black holes in the universe. Some mergers involve black holes with unexpected masses. Others show evidence of rapid rotation or unusual spin orientations. But all of them behave exactly as general relativity predicts. These gravitational wave observations provide the most direct evidence that black hole gravitational fields arise from space-time curvature outside the event horizon. The waves are generated by the changing curvature pattern as two separate black holes spiral together and merge. At no point in this process does any influence need to escape from inside the event horizons. The merger process can be understood entirely in terms of the interaction between the external gravitational fields of the two black holes. As they orbit each other, their individual curvature patterns combine to create a time-varying geometry that radiates energy in the form of gravitational waves. Even during the final merger, when the event horizons themselves touch and combine, the gravitational wave emission arises from the changing geometry outside the merged horizon. The newly formed black hole goes through a settling process, radiating away any asymmetries in its shape through gravitational wave emission. But this radiation comes from the external space-time geometry, not from the interior. All of these observations, from stellar orbits to gravitational lensing, to direct imaging to gravitational wave detection, paint a consistent picture. Black holes exert gravitational influence through the curvature of space-time outside their event horizons. This influence was established during the black hole formation process and persists as a permanent feature of space-time geometry. There's no evidence for any gravitational effects that would require communication from inside black holes to the outside universe. No deviations from general relativity that might suggest exotic physics, allowing faster than light information transfer. No anomalies that would indicate gravitational signals somehow escaping from behind event horizons. Instead, every observation confirms that gravity around black holes works exactly as our theoretical understanding predicts. The gravitational influence extends far beyond the black holes themselves, but it arises entirely from the curved space-time geometry that exists outside the point of no return. This observational confirmation provides the final piece of evidence for resolving our original paradox. We don't need to wonder how gravity escapes from black holes, because we can see directly that it doesn't need to escape. The gravitational effects we observe arise from the permanent curvature of space-time that black holes create in the regions where we can actually observe those effects. After exploring the theoretical foundations and observational evidence, we can now provide a definitive answer to our original question. Gravity doesn't escape from black holes because it was never inside them to begin with. The gravitational influence we observe around black holes is the permanent signature left in space-time geometry during their formation, a fossil record written in the curvature of space and time itself. To understand this resolution completely, we need to trace through the entire process of black hole formation from beginning to end. Imagine we're watching a massive star, perhaps 25 times the mass of our Sun, as it reaches the final moments of its life. For millions of years, this star has maintained a delicate balance between the outward pressure of nuclear fusion and the inward pull of its own gravity. But nuclear fuel is finite, and when the star exhausts its ability to generate energy through fusion reactions, gravity wins the cosmic battle decisively. The star's core, once supported by the intense pressure of nuclear fires, suddenly collapses under its own weight. What happens next occurs so rapidly that human minds can barely comprehend the timescales involved. In less than 1 second, the stellar core shrinks from the size of Earth to a region smaller than a city. The density reaches levels so extreme that atomic nuclei are crushed together, and even the strong nuclear force that holds protons and neutrons together is overwhelmed by gravitational compression. The collapse continues until general relativity predicts the formation of a singularity, a point of infinite density where the known laws of physics break down. But the key insight for our gravitational paradox is what happens to space-time during this collapse. The massive star was already curving space-time before the collapse began. Its 25 solar masses created a gravitational well that extended far into space, influencing the orbits of any planets or companion stars in the system. As the collapse proceeds, this space-time curvature doesn't disappear. Instead, it gets compressed along with the collapsing matter, becoming more and more concentrated near the center of the system. But the total amount of curvature, as measured by observers far from the collapsing star, remains essentially unchanged. This is a consequence of a fundamental principle in general relativity called Birkhoff's theorem, which states that the gravitational field outside any spherically symmetric mass distribution depends only on the total mass, not on how that mass is distributed internally. Whether the 25 solar masses are spread out as a giant star or compressed into a microscopic black hole, the space-time curvature at any given distance from the center remains the same. From the perspective of a distant observer watching this collapse, something remarkable happens to the information about the gravitational field. As the stellar surface approaches what will become the event horizon, light rays trying to escape become increasingly redshifted and time-dilated. The last photons to escape carry with them the final information about the matter distribution that will ever reach the outside universe. This final burst of electromagnetic radiation, stretched to infinite wavelengths and carrying infinitely redshifted information, becomes frozen at the event horizon from the perspective of external observers. The gravitational field pattern established by this last escaping information becomes permanently embedded in the space-time geometry outside the newly formed black hole. It's important to understand that this freezing process isn't just a visual effect or an artifact of how we observe the collapse. It represents a fundamental aspect of how information and causality work in curved space-time. The event horizon marks the boundary beyond which no information can ever escape. So the gravitational field outside that boundary must be determined entirely by information that escaped before the boundary formed. This frozen field concept explains why black holes appear to remember certain properties of the matter that formed them, even after that matter has disappeared behind the event horizon. The black hole's mass, for example, equals the total mass energy of everything that fell into it, as measured by the curvature of space-time outside the horizon. Similarly, if the collapsing star was rotating, the black hole inherits that angular momentum as a permanent feature of its external space-time geometry. The rotation creates frame-dragging effects that twist space-time around the black hole, causing nearby objects to be dragged along in the direction of rotation, even if they're trying to remain stationary. But according to the no-hair theorem, these are the only properties that survive the collapse process. Any other details about the original star, its chemical composition, its magnetic field structure, its surface temperature, all of this information either gets radiated away during the collapse or falls behind the event horizon, where it can no longer influence the outside universe. The mathematical description of the final state is remarkably simple. A non-rotating black hole is described completely by the Schwarzschild metric, a solution to Einstein's field equations that depends only on the black hole's mass. A rotating black hole is described by the Kerr metric, which adds the black hole's angular momentum as a second parameter. These metrics describe the curvature of space-time outside the event horizon with mathematical precision. Every gravitational effect we can observe, from the bending of light rays to the precession of orbital ellipses to the emission of gravitational waves during mergers, can be calculated directly from these geometric descriptions. The beauty of this picture is its universality. Every black hole in the universe, regardless of how it formed or what fell into it, has an external gravitational field described by one of these simple metrics. A black hole formed from the collapse of a massive star has the same external geometry as one formed from the gradual accretion of matter over millions of years, as long as the final mass and spin are the same. This universality has been confirmed by every astronomical observation we've discussed. The black hole at the center of our galaxy, formed billions of years ago through processes we can only guess at, behaves exactly like the black holes detected through gravitational waves, which formed from stellar collapse within the last few billion years. The concept of frozen gravitational fields also explains why black holes can exist for virtually unlimited periods without losing their gravitational influence. Unlike electromagnetic fields, which require continuous currents to maintain themselves, or sound waves, which gradually dissipate their energy to the surrounding medium, gravitational fields are built into the permanent architecture of space-time. Once established, the curvature pattern around a black hole costs no energy to maintain. It's as permanent as the geometry of space itself. A black hole could sit alone in empty space for trillions of years, and its gravitational field would remain unchanged, ready to influence any matter or energy that happened to pass nearby. This permanence isn't just theoretical speculation. We can observe black holes that formed in the early universe less than 1 billion years after the Big Bang, and their gravitational fields show no signs of weakening or decay. Ancient quasars powered by supermassive black holes continue to gravitationally lens background galaxies with precisely the strength we'd expect based on their estimated masses. The implications of this picture extend far beyond just understanding black holes. It reveals something profound about the relationship between matter, energy, and space-time itself. Matter and energy curve space-time. But once that curvature is established, it can persist long after the original matter and energy have transformed into other forms, or become causally disconnected from external observers. This suggests that space-time has a kind of memory, a capacity to store information about past events in its geometric structure. The gravitational waves we detect from ancient black hole mergers carry information about cosmic collisions that happened billions of years ago, preserved with almost perfect fidelity in the curvature patterns of space-time. But this memory is highly selective. Space-time remembers only the most basic properties of mass, energy, momentum, and angular momentum. All the complex details of how matter and energy are organized, their quantum states, their chemical compositions, their thermal properties, these get lost either to radiation or to causal disconnection behind event horizons. This selective memory of space-time geometry provides a new perspective on why the gravitational paradox seems so puzzling in the first place. We're used to thinking of forces and influences as things that must be continuously transmitted from source to target. If you want to push on something, you have to maintain contact with it. If you want to send a radio signal, you have to keep transmitting. But gravity isn't a force in this conventional sense. It's the shape of the stage on which all physics takes place. Asking how gravity escapes from a black hole is like asking how the shape of a bowl continues to hold water after you've removed your hands from the pottery wheel. The shape doesn't need to be continuously created or maintained. It's a permanent feature of the object's geometry. The analogy isn't perfect because space-time is far more dynamic and responsive than any material object. But it captures the essential insight that gravitational influence arises from geometric relationships, not from the transmission of signals or forces. This geometric understanding of gravity also explains why Einstein's theory has been so remarkably successful at predicting the behavior of black holes. The theory doesn't treat gravity as a force acting between distant objects, but as a manifestation of the curvature properties of space-time itself. This geometric approach naturally leads to the conclusion that gravitational influence can exist wherever space-time is curved, regardless of whether the source of that curvature is causally connected to external observers. The resolution of our paradox thus brings us to a deeper appreciation of what Einstein accomplished with general relativity. He didn't just provide a more accurate description of gravitational phenomena, he revealed that gravity reflects the fundamental geometric structure of the universe itself. In this geometric picture, black holes aren't mysterious objects that somehow violate the rules of physics by allowing gravity to escape while trapping everything else. Instead, they're natural consequences of Einstein's equations, regions where space-time curvature becomes so extreme that it creates permanent geometric features that influence the surrounding universe for billions of years. The gravitational influence we observe around black holes is thus not something that escapes from their interiors, but something that was established in their exteriors during the formation process and remains there as a permanent feature of space-time geometry. The black hole itself is this curvature, this permanent distortion in the fabric of space and time that we call the gravitational field. Our journey through the black hole gravitational paradox has led us to profound insights about the nature of reality itself. The resolution reveals that gravity isn't just another force like electromagnetism or the nuclear forces, but something far more fundamental. It's the geometric structure of space-time, the very stage upon which all physics unfolds. Understanding this distinction transforms our entire perspective on the universe and our place within it. The implications begin with a radical reconceptualization of what we mean by space and time. In our everyday experience, space seems like an empty container, a passive backdrop against which objects move and interact. Time appears to flow uniformly, providing a universal rhythm that synchronizes all events. This intuitive picture, formalized by Newton in the 17th century, served physics well for over 2 centuries. But Einstein's insights revealed that this intuitive picture is fundamentally wrong. Space and time aren't separate, absolute entities. Instead, they're woven together into a single 4-dimensional fabric called space-time. And this fabric is anything but passive. It responds dynamically to the presence of matter and energy, curving and flexing in ways that determine how everything else behaves. This dynamic relationship between matter and space-time geometry is encapsulated in John Wheeler's famous summary of general relativity. Matter tells space-time how to curve, and curved space-time tells matter how to move. This simple statement contains the key to understanding not just black holes, but the entire structure of the universe. When we apply this principle to black holes, the paradox dissolves completely. Black holes don't need to send gravitational signals from their interiors because they are the curvature of space-time itself. The gravitational influence we observe isn't something that emanates from the black hole like light from a star. Instead, it's the permanent geometric distortion that the black hole's formation created in the fabric of space-time. This geometric understanding of gravity has implications that extend far beyond black holes. It suggests that everything we experience as physical reality emerges from the underlying geometry of space-time. The forces that hold atoms together, the momentum that carries planets around stars, even the flow of time itself, all of these phenomena arise from the curvature properties of the 4-dimensional space-time manifold. Consider what this means for our understanding of causality and information flow in the universe. In Newton's picture, gravitational influence could propagate instantly across any distance, creating the troubling possibility of faster-than-light communication. But Einstein's geometric view naturally incorporates the light speed limit into the fundamental structure of space-time itself. Changes in space-time curvature propagate as gravitational waves traveling at exactly the speed of light. This isn't just a convenient mathematical result, it's a deep statement about the unified nature of space, time, and causality. The same geometric structure that defines the shortest path between 2 points also determines the maximum speed at which information can travel between them. This unification of geometry and physics reveals why black holes can have such profound gravitational influence without violating causality. The influence doesn't travel from inside the black hole to external objects. Instead, both the black hole and the external objects exist within the same curved space-time geometry, and their interactions are determined by the geometric relationships encoded in that curvature. The permanence of gravitational fields around black holes also tells us something remarkable about the nature of information and memory in the universe. Unlike other physical fields, which require ongoing energy input to maintain themselves, gravitational fields become permanent features of space-time geometry once they're established. This gives space-time itself a kind of memory, an ability to preserve information about past events in its geometric structure. The gravitational waves that LIGO detects carry information about black hole mergers that occurred billions of years ago, preserved with extraordinary fidelity in the curvature patterns of space-time. But this memory is highly selective. Space-time remembers only the most basic properties of mass, energy, momentum, and angular momentum. All the complex details of how matter and energy are organized get lost, either radiated away or trapped behind event horizons where they can no longer influence external observers. This selective memory principle, embodied in the No-Hair theorem for black holes, suggests something profound about the relationship between complexity and fundamental physics. As we probe deeper into the structure of reality, the incredible complexity we see at the surface level gives way to simpler and more universal principles. The billions of stars in a galaxy, each with its own complex internal structure and evolutionary history, collectively create a space-time curvature pattern that can be described by just a few numbers representing the galaxy's total mass and angular momentum. The incomprehensible complexity of the matter that falls into a black hole gets reduced to 3 simple parameters: mass, charge, and spin. This tendency towards simplification at the deepest levels isn't just a mathematical convenience. It reflects something fundamental about how information flows in the universe. As systems become more gravitationally extreme, they naturally evolve toward configurations that can be described by the minimum possible amount of information. The holographic principle, suggested by black hole thermodynamics and supported by string theory calculations, takes this idea even further. It proposes that all the information in any region of space can be encoded on the boundary of that region, much like a hologram encodes 3-dimensional images on a 2-dimensional surface. If the holographic principle is correct, then the 3-dimensional reality we experience might be a projection of information processing occurring on a distant 2-dimensional boundary. The black holes within our 3-dimensional space would themselves be holographic projections, their gravitational influence arising from the encoding of mass and energy information on this boundary surface. This holographic picture provides a radically different perspective on the black hole gravitational paradox. Instead of asking how gravity escapes from inside black holes, we might ask how the holographic encoding of gravitational information on boundary surfaces creates the illusion of 3-dimensional black holes with interior regions. Even more spectonding ideas emerge from attempts to understand the quantum nature of space-time itself. Loop quantum gravity suggests that space and time are made up of discrete units connected in a network-like pattern, with smooth space-time geometry emerging only as an approximation when we consider large numbers of these discrete elements. In this picture, black holes might be understood as particular configurations of the underlying discrete network, with their gravitational influence arising from the way information flows through the network connections. The event horizon would represent a boundary in the network where information flow becomes unidirectional. But the gravitational effects would still arise from the network structure outside this boundary. Causal set theory offers another perspective on discrete space-time, suggesting that the fundamental reality consists of discrete events connected by causal relationships. In this framework, smooth space-time and continuous gravitational fields would be emergent properties that appear when we consider large numbers of discrete causal connections. These quantum approaches to space-time suggest that our entire discussion of black holes and gravitational fields might be describing emergent phenomena rather than fundamental reality. The black holes we observe might be particular patterns in an underlying quantum system, with their gravitational influence arising from the way quantum information is processed and organized in that system. But regardless of which approach ultimately proves correct, they all preserve the basic insight that gravitational influence doesn't require communication from inside black holes to external observers. Whether gravity arises from smooth space-time curvature, holographic boundary encoding, discrete network connections, or quantum information processing, the influence we observe around black holes comes from the geometric or informational structure that exists in regions causally connected to external observers. This brings us to perhaps the most profound implication of our investigation. The resolution of the black hole gravitational paradox reveals that asking how gravity escapes from black holes reflects a fundamental misunderstanding of what gravity actually is. Gravity isn't something that moves through space like light or sound. Instead, it is the structure of space itself. This realization forces us to reconsider our entire conceptual framework for understanding the universe. We typically think in terms of objects existing in space and time, interacting through forces that propagate between them. But the geometric view of gravity suggests that this picture puts the cart before the horse. Perhaps it's more accurate to say that space-time geometry is primary, and what we call objects and forces are secondary phenomena that arise from particular configurations of this underlying geometric structure. Matter and energy don't exist in space-time so much as they are particular patterns of space-time curvature. From this perspective, asking how gravity escapes from a black hole is like asking how the curvature of a sphere manages to influence the paths of curves drawn on its surface. The curvature doesn't escape from anywhere because it isn't located at any particular point. Instead, it's a global property of the geometric structure that influences everything embedded within that structure. This geometric understanding of reality connects to some of the deepest questions in physics and philosophy. If space-time geometry is fundamental, what determines the properties of this geometry? Why does space-time have 4 dimensions rather than some other number? Why do the laws of physics take the particular mathematical forms that they do? These questions push us toward even more fundamental theories that might explain the structure of space-time itself. String theory suggests that space-time might emerge from the dynamics of tiny vibrating strings in higher dimensional space. Loop quantum gravity proposes that space-time is built up from discrete quantum units. Other approaches explore the possibility that space-time is a holographic projection or an emergent property of quantum information processing. But even as we probe these deeper levels, the lesson from black holes remains relevant. Whatever the ultimate nature of reality, the phenomena we observe arise from structural relationships, rather than from the transmission of influences between separate objects. The gravitational effects around black holes teach us that the universe is far more interconnected and unified than our everyday experience suggests. The black hole gravitational paradox thus serves as a gateway to understanding some of the most profound questions about the nature of reality. It shows us that space and time are not passive containers for physical events, but active participants in determining how those events unfold. It reveals that gravity connects geometry, causality, and information in ways that challenge our deepest assumptions about how the universe works. Most importantly, it demonstrates that apparent paradoxes in physics often arise not from contradictions in nature, but from limitations in our conceptual frameworks. By expanding our understanding of what gravity actually is, we resolve not just the black hole paradox, but gain insight into the geometric foundations of reality itself. If light can't escape a black hole, how can gravity? It doesn't have to. It never left. The black hole's pull is not a message from within, it's the permanent curve it left on the space around it. And that curve is space-time itself. Our journey through this apparent paradox has taken us from the event horizons of black holes to the very foundations of reality. We've discovered that the question itself was based on a fundamental misunderstanding, a remnant of older ideas about how forces work in the universe. The resolution reveals something far more beautiful and profound than we might have expected. Gravity doesn't escape from black holes because gravity isn't something that needs to escape. It's not a signal broadcast from inside the event horizon, not a force transmitted across space, not a message sent from the black hole's interior to the outside universe. Instead, gravity is the shape of space-time itself, the geometric structure within which all physics unfolds. When a massive star collapses to form a black hole, it doesn't trap its gravitational influence behind the event horizon. Instead, the collapsing matter curves space-time in its vicinity, and this curvature becomes a permanent feature of the geometric landscape. The event horizon prevents new information from escaping, but the gravitational field was never inside to begin with. It exists in the curved space-time outside the horizon, where it was established during the collapse process. This curved space-time doesn't require ongoing maintenance or continuous communication from the black hole's interior. Like the shape of a mountain or the curve of a river valley, it's a structural feature that persists as long as the geometry itself remains stable. The gravitational influence we observe around black holes is this persistent curvature, frozen into the fabric of space and time during the black hole's formation. The beauty of this resolution lies in its universality. Every black hole in the universe, regardless of how it formed or what fell into it, creates the same type of space-time curvature outside its event horizon. This curvature is described by surprisingly simple mathematical expressions that depend only on the black hole's mass, spin, and electric charge. All the complex details of the original matter get erased, leaving behind only these basic geometric parameters. This universality has been confirmed by decades of astronomical observations. From the precise orbits of stars around the supermassive black hole at our galaxy's center, to the gravitational wave signals from merging black holes billions of light years away, every observation matches the predictions of Einstein's geometric theory of gravity with remarkable precision. The Event Horizon Telescope has even allowed us to see the shadows cast by black holes, direct visual evidence of how their extreme space-time curvature bends light rays and creates the dark regions from which no photons can escape. These images confirm that real black holes behave exactly as general relativity predicts, with no anomalies or deviations that might suggest exotic physics. But our investigation has revealed more than just the solution to a single paradox. It has shown us that gravity connects geometry, time, and causality in ways that transform our understanding of reality itself. The same curved space-time that creates gravitational attraction also determines how fast time flows, how distances are measured, and what paths light rays follow through the universe. This geometric view of gravity explains why Einstein's theory has been so remarkably successful at describing everything from the precession of Mercury's orbit to the expansion of the universe itself. It's not just a more accurate description of gravitational phenomena, it's a fundamental insight into the structure of space-time and the nature of physical law. The resolution also illuminates the deep connection between information, causality, and geometry in physics. Event horizons prevent information from escaping black hole interiors, but they don't prevent the geometric relationships established outside those horizons from influencing the surrounding universe. This distinction between information flow and geometric structure helps us understand how black holes can have such profound effects while maintaining strict causal boundaries. Even the most exotic theoretical proposals, from wormholes to holographic space-time to quantum gravity, preserve this basic causal structure. While they might suggest radical new ideas about the fundamental nature of space and time, they don't allow gravitational influence to escape from inside black holes faster than light. The geometric principle remains robust across all these different approaches to understanding gravity. Perhaps most importantly, our journey has shown us that apparent paradoxes in physics often arise not from contradictions in nature, but from limitations in our conceptual frameworks. The black hole. Gravitational paradox seem puzzling only because we were thinking about gravity in terms of forces and signals, rather than geometry and space-time curvature. This lesson extends far beyond black holes to many other areas of physics, where apparent contradictions dissolve once we adopt the right conceptual framework. Quantum mechanics seems paradoxical until we abandon classical ideas about definite particle properties. Relativity seems impossible until we give up absolute notions of space and time. The history of physics is filled with such conceptual revolutions. The black hole paradox also connects to some of the deepest ongoing questions in theoretical physics. The information paradox, the nature of quantum gravity, the holographic principle, and the emergence of space-time itself all involve similar questions about the relationship between geometry, information, and causality. As we push toward even more fundamental theories of reality, the insights we've gained from studying black holes will likely prove crucial. They show us that space-time is far more dynamic and responsive than our everyday experience suggests, and that the phenomena we observe arise from structural relationships rather than from the exchange of forces between separate objects. The gravitational influence of black holes thus serves as a window into the deepest levels of physical reality. It reveals that the universe is not a collection of objects moving through empty space, but a unified geometric structure where matter, energy, space, and time are all aspects of a single underlying reality. In the end, the question that began our investigation, how can gravity escape from a black hole when nothing else can, finds its answer in a profound truth about the nature of gravity itself. Gravity doesn't escape because it doesn't need to. It was never inside to begin with. It is the shape of the universe, the curve of space-time, the geometric stage on which all of physics performs its cosmic dance. And that stage, once shaped by the collapse of a massive star into a black hole, remembers that shaping for billions of years. The gravitational influence we observe is not a signal from the black hole's mysterious interior, but the permanent signature of its formation, written in the curvature of space-time itself and persisting as long as the black hole exists. This understanding transforms our view of black holes from mysterious objects that somehow violate the laws of physics into natural expressions of those laws at their most extreme. They are not anomalies in the fabric of space-time, but fundamental features of it, cosmic laboratories where the geometric nature of gravity reveals itself most clearly. The gravity that shapes our universe, that holds galaxies together and guides the dance of stars and planets, is the same gravity that curves space-time around black holes. It never left because it was always there, woven into the very structure of reality itself. In understanding this, we glimpse something profound about our universe, that beneath all its complexity and mystery lies a deep geometric elegance that connects the smallest quantum fluctuations to the grandest cosmic structures. The black hole's gravitational pull is thus not a message from beyond the point of no return, but a permanent testament to the power of matter to shape space-time, and of space-time to preserve that shaping across the vast scales of cosmic time. It is gravity in its purest form, geometry made manifest, the universe's way of remembering the star that once was, and honoring it with an influence that will persist until the very end of time.